So our second speaker this morning is Jo Nelson of Rice University, and she will tell us about equivariant and non-equivariant contact homology.
Thanks. And I guess maybe at this moment, before we forget, we should thank the organizers for organizing such a lovely conference and summer school. Okay, so last week I gave some lectures about cylindrical contact homology, so I won't sort of reprise everything. Apparently one of the videos already has 2,800 views, which I don't know how is possible, but they exist. So I'm going to give kind of like a quick review of what people were trying to do at the turn of the century, and then discuss some recent work with Michael Hutchings, where we figure out a way to move past some of the transversality and compactness issues and get sort of richer flavors of cylindrical contact homology, which is this S1 equivariant and non-equivariant version. Okay, so to set notation, I'm going to let M2n plus 1 be my contact manifold. And it's going to be a closed, oriented contact manifold. And then I'm going to assume that the defining one form is non-degenerate. And I think we all know this, but lambda contact means that lambda wedge d lambda to the n is a volume form, which is the same thing as saying that d lambda restricted to its kernel is a symplectic or non-degenerate. And then there's a unique vector field that's determined by the choice of your contact form that plays the role of a Hamiltonian vector field in the contact world. So the Rabe vector field, this is uniquely determined by lambda of r is equal to 1, and then you want the contraction of r with d lambda to be 0. So this lambda of r equals 1 is a normalization condition, and then the contraction of r with d lambda being 0 tells you that the Rabe vector field is transverse to the hyperplane distribution, and this gives you a splitting of your contact manifold, the tangent space, into the contact distribution plus the Rabe direction. And then because I'm going to be constructing a Floer type homology theory, I need a choice of J. So because I have a symplectic vector space given by the kernel of lambda, which is Xi paired with d lambda, I can extend a d lambda compatible almost complex structure on the symplectic vector bundle to 1 on the symplectization. And this compatibility sort of adjective just says that I'm getting a Riemannian metric when I pair J with my contact form. And this is going to be a translation, invariant, and extension of my complex structure on the contact distribution. So I want J restricted to Xi to be this original J that I picked. And then I want to intertwine this Rabe direction with the R direction of the symplectization. So I want J of dd tau to be equal to R, where tau is my coordinate on R. And then that's going to allow me to look at moduli spaces of pseudo-holomorphic curves in the symplectization. So gamma plus and gamma minus are going to be closed Rabe orbits of my Rabe vector field. And this moduli space is going to consist of maps from the cylinder into the symplectization. So we want the d bar equation to be satisfied. And then we want asymptotics. So we want the limit as s goes to plus or minus infinity of the projection of r of our curve. So here s is the r component, t is the s1 coordinate, and when I project my curve to the r component of my symplectization, I want to get plus or minus infinity. And then if I look at the limit as s goes to plus or minus infinity of pi m u, this needs to be a parametrization of the Rabe orbits. And then I'm going to mod out by the automorphism group of the domain, which is r cross s1. And I have another r action on the symplectization. So I'm going to write this as m twiddle because I haven't modded out by this r action on the symplectization. So the picture that you draw is you pretend that your contact manifold is a boring circle. And this is r cross m. And then your J holomorphic curve limits on gamma plus at plus infinity and gamma minus at negative infinity. And so that's the sort of schematic picture. And Hofer, Vysotsky, and Zander kind of started studying these types of moduli spaces. There were sort of, at the time, not really restrictions on genus, and you could have an arbitrary number of negative or positive ends, and they kind of set up the Fredholm theory for the space of somewhere injective curves. And then they used it to prove a number of really nice dynamical results, which have been touched on by various people on this conference. Okay, so MJ is just going to be this M twiddle. And I'm going to mod out by the automorphisms of R. And then the virtual dimension of MJ is going to be the Conley-Zander index of the Rabe orbit at the top minus the Conley-Zander index of the Rabe orbit at the bottom, minus 1 because of this modding out by this automorphism group of R, which has dimension 1. And then I have a first Chern class term, which depends on the trivialization, as do these Conley-Zander index terms of U pullback of Xi. But usually you can pick a nice trivialization so that you can just make this term be 0, and then you can ignore it for the rest of the sort of time. Okay, so then the sort of hope was that in 2000, among other things, Eli Ashberg, Giventhal, and Hofer conjectured that you could form a chain complex and for a closed non-degenerate contact manifold, you could form a chain complex generated by the closed Rabe orbits, and then the differential would be a weighted count of elements of this moduli space. So I'll write this as CEGH, and this was going to be generated as a vector space over Q by the good Rabe orbits. Okay, and this good has to do with being able to orient the moduli spaces, and the cylindrical contact homology theory that they came up with is kind of a weird orbifold homology theory, and so there's always this kind of, you have to throw out certain generators if they screw up your orientations and stuff. So let me quickly say what a good Rabe orbit is. So basically, if gamma is embedded, then either the Conley-Zander index of gamma to the 2k mod 2 is equal to the Conley-Zander index of gamma to the 2k plus 1. And I guess let's make this a plus 1 and a plus 2. so that you can start off at k equals 0. Or you do not have equality. So what this is saying is that when you iterate your closed Rabe orbit, either the parity of the Conley danger index remains the same or it changes. And in the latter case, all even iterates of gamma are said to be bad. Otherwise, if a Rabe orbit is not bad, it is said to be good. And in symplectic homology, these bad Rabe orbits are contributing Z mod 2 torsion, and sort of that's related to, like, you're kind of throwing them out because this theory is supposed to only be defined with coefficients over Q, and there's just kind of some weird things going on. And then there's an explicit example of a period doubling bifurcation where you have the same context structure, and locally you can deform it so that in the neighborhood of an elliptic orbit of a certain period, you can produce a negative hyperbolic orbit of half the period, as well as an elliptic orbit of the same period, and you can sort of check that if you include the even iterates of the negative hyperbolic orbit, you will not have a chain complex that's invariant under this period doubling bifurcation, which is bad if you want a contact homology theory that's an invariant of your contact distribution. So it's kind of like this good-bad thing is a little bit mysterious, but it eventually makes sense, and mostly it means that you just have a lot of headaches with Z mod 2 and orientations. Okay, and then another kind of weird thing is that the grading on this theory is given by the Conley danger index, but it's shifted by the dimension of the manifold, where n is back to this manifold is given by dimension 2n plus 1, and in dimension 3, your n would be equal to, oh, this is supposed to be, sorry, 2n minus 1 to get this grading to be correct. The grading is given by Conley danger index of gamma minus 1. Okay. And so you see kind of the dynamically convex assumption will show up because this will sort of give us grading at least 2, and it allows us to rule out certain compactification issues with contractible Rabe orbits. Uh-huh. Oh, yeah, that's a good point. Thanks, Vinny. Okay. And, right, if we look at the linearized return map, of gamma restricted to the hyperplane distribution, then even covers of orbits with a odd number of pairs of negative real eigenvalues are going to be the bad orbits. And this is related to the sort of how the chain complex in ECH is generated, where in 3 dimensions, when you restrict to the contact distribution, your linearized return map is just going to be some symplectic matrix of dimension 2. And then we know that if the symplectic matrix can't have 1 as an eigenvalue, it has to have either complex or real eigenvalues. And the way to get the determinant to be 1 is to either have pairs of complex eigenvalues, then your Rabe orbit is said to be elliptic. If you have positive real eigenvalues, then you're a positive hyperbolic orbit. If you have negative real eigenvalues, you're a negative hyperbolic orbit. and then the positive iterates of the even iterates of the negative hyperbolic orbits are going to be your bad ray orbits. And so this is also kind of related to why the generators in ECH are the way that they are. Okay. And now I can tell you what the differential is supposed to be. So there's going to be two sort of ways to define the differential. One way allows you to look at the multiplicity of the top of your cylinder, and the other way will encode the multiplicity of the bottom of your cylinder. So here's my cylinder, x, y. So this could be a K-fold cover of a somewhere injective cylinder. Okay, and so then you can sum over the y's of index difference 1, and then you want u to be in this moduli space connecting x to y, and then the coefficient is going to be multiplicity of the top Rabe orbit divided by multiplicity of the cylinder, and then you have some choice of coherent orientations to orient your cylinder. And then the other way to define the differential is to encode the multiplicity of the bottom. Okay. And so what's kind of weird is that you have these weighted counts, but they're actually going to be integral because in this case, our cylinder would have multiplicity k, but the multiplicity of x would be kp, multiplicity of y would be kq, and in either case, the k divides kp or kq. And the kind of or I don't know exactly what to say, but you could conceivably end up with the homology with respect to this differential being different with respect to this differential if you work over z coefficients, because you could end up with different torsion elements. And in order to get the chain maps and the chain homotopy to work, you have to be able to divide and multiply by multiplicities of cylinders and orbits. And so that's part of the reason as well why we want this vector space, we want this chain complex to be generated over Q. So there are many kind of like weird things with this theory, which are not so satisfying. Okay, so then the congerum from 2000 was assume no contractible Rabe orbits of grading, this shifted grading in terms of the Conley-Zander index, -1, 0, or 1. Then the differential is well defined. D squared is 0, and the homology of this chain complex, which depended on J, lambda, doesn't actually depend on the choice of lambda or J. So you get a contact invariant. And it was kind of a congerum because there wasn't the appropriate, I don't know, Kurnishi, polyfold, whatever machinery to achieve transversality for your multiply covered curves. But there was some hope that it could be done. But it seems like people were maybe a little bit too optimistic at the turn of the century. So there has been a little bit of progress. So let me briefly say that, so Hutchings and Nelson and me have a paper from 14 where we show in dimension 3, if the Conley-Zander index of gamma contractible is greater than or equal to 3, which is basically the dynamically convex condition, then for generic J, the differential is well defined, and d squared is equal to 0. But we couldn't prove invariance because our sort of toolkit of low-dimensional techniques failed in a cobordism, and so that led us to the project that I'll talk about now. And then the kind of other partial results that people had involved excluding all contractible Rabe orbits. So Bao Honda have a paper from 2015 in dimension 3 in the hypertight case. They construct basically a contact invariant, which by later work of Hutchings and I, we can show is actually isomorphic to the original definition of Eliashberg, Giventhal, and Hofer. And they show that their sort of version, which depends on taking a lot of perturbations locally, gives you a contact invariant because they basically perturb away all of the elliptic Rabe orbits into hyperbolic ones. And then using an obstruction bundle gluing correction term, you can compute the chain homotopy. And then Pardon, with his Kernishi Atlas stuff, so I think this is 2015, this works in any dimension in the hypertight case. But you can't sort of directly compute the differential because you're doing an abstract perturbation of the Cauchy-Riemann equation, and so it will tell you that you have an invariant, but you may not be able to compute it. And here, hypertight just means that you have no contractible Rabe orbits. And then in the meantime, the substitute that people have been using, which is well defined and works quite well, is the positive part of S1 equivariant symplectic homology. The sort of downside of that theory is that it's quite a bit more difficult to actually compute because it's defined in terms of a direct limit of Hamiltonians. And so the theory is all well defined, but you take a direct limit of Hamiltonians so that the time one periodic orbits will be Rabe orbits of sort of increasing iteration. And by taking a direct limit over all these Hamiltonians of increasing slopes, you get the whole theory. But this typically needs a filling for your symplectic manifold, and then to compute it, you have to really dig through pages of spectral sequences, which you can see in some of the work by Jean Gut, and then also Leonardo and Miguel and Otto van Kurt and others. So it is kind of possible to use this theory, but it requires a lot more sort of effort and going through like pages and pages of spectral sequences. So kind of the, motivation for the next part is to try to find a way to define a contact invariant in the same spirit where you're counting J-holomorphic curves in your chain complexes generated by Rabe orbits, which avoids sort of the transversality issues with multiply covered curves. So the idea that Michael and I had was to use a domain dependent, so that's going to be an S1 dependent, almost complex structure. It's going to be a family of lambda compatible almost complex structures. So I'll write this as a boldface J, and each JT is going to be lambda compatible and generic. And then what I do is I replace this moduli space with this family of time-dependent almost complex structures. So I'll put a boldface J here. Now I have my family. Now I put a T here. And now I no longer can mod out by the automorphism group of S1 because my J depends on S1. And so what happens is that when I look at the virtual dimension of this moduli space, I have to increase its dimension by 1. So this minus 1 goes away. And so that's a little bit, I don't know. I no longer find it disturbing, but when you first look at this, it makes you think that constructing a differential is going to be a little bit more tricky, because the way that you want your differential to be well defined is you want it to count a discrete set of points, meaning you want your moduli space to, you want it to count elements of a zero-dimensional moduli space. But now to get the moduli space to have zero dimension, the Conley-Zander index of the top and the bottom has to be equal, and that's not really so satisfying. So, and then also you would not necessarily be able to show that that differential squares to zero and whatnot. So what you can do is kind of go back to what the Morse-Bott situation is like, just when you think about this cylindrical contact homology theory. Like, you can kind of interpret some of the failure of transversality as a degenerate situation, and you can think of each of the generators of your chain complex as sort of a Bott manifold. And so then the idea would be, what is the algebra associated to perturbing this sort of Bott manifold? Well, if you have a circle and that's your generator, you could put the height function on it, and then that would give rise to two generators for each of your Rabe orbits. So you kind of run with that idea. And then also, because we're trying to we're breaking this S1 symmetry, that means that we kind of also want to break the symmetry of these Rabe orbits, and so we can do that by introducing evaluation maps and looking at what happens when we plug in U of 0 cross R and seeing what happens. So let me write this stuff down. Okay, so Ev plus minus is going to be a map from M tilde J, gamma plus minus, to the image of your Rabe orbit, and then Ev plus is going to be limit as s goes to plus infinity. Ev minus is going to be limit as s goes to minus infinity of the projection of your curve to M, where you put in S0. So you're basically looking at your cylinder, and you look at U of R cross 0. That's going to be some line. Ev plus is going to be the point at the top, and Ev minus is going to be the point at the bottom. And so using these evaluation maps, you could then consider a moduli space where the index difference of the Conley-Zander indices is 1, and then by imposing a point constraint at the top or a point constraint at the bottom, that would cut down the dimension by 1, and you'd be looking at a zero-dimensional moduli space. And sort of the first idea may be, well, let's just put a point constraint in the top and see what happens. But unfortunately, if you try to prove that d squared is 0, you're going to see that it doesn't work out, because when you try to compactify a space of cylinders with a point constraint at the top, they can break with different sort of cyclic point constraints in the center, which is not encoded in your differential, so you're not going to be able to prove that d squared is 0. So you're going to have to go back to the abstract Morse-Bott formalism when your Bott manifolds are all circles, and that will kind of tell you what you should make your chain complex. So the non-equivariant chain complex is going to be generated by all Rabe orbits, which is nice because you know that in symplectic homology, the bad Rabe orbits contribute torsion, and it kind of has twice as many generators as the cylindrical theory. And we're going to have two sort of formal symbols, gamma check and gamma hat, and those correspond to putting this sort of height function on the Bott manifold, which is a circle, except your height function would have sort of the max and the min arbitrarily close to each other, so that when you just consider the algebraic formalism, each generator, which is your Bott manifold, gives rise to two generators, one which will have the grading artificially shifted up by 1 because it corresponds kind of to the max, and the other one with the same grading. So here, gamma check and gamma hat are formal symbols where the grading of gamma check is the same as the grading of gamma, which is this Conley-Zander index plus n minus 3. And then the grading of gamma hat is equal to gamma check plus 1. And sort of for each embedded orbit gamma, you can think of gamma check as living in the 0th homology group of the image of gamma, and gamma hat as living in the 1st homology group of the image of gamma. So it's just kind of a Morse-bot construction, which is, we're not sort of setting up the analysis to be Morse-bot, we're just seeing what the formalism from sort of Morse-bot land should tell us about how to construct the differential. Oh, and I guess, sorry. This is true regardless if gamma is embedded or not. Okay. So the way that I'm going to define the differential is in terms of 4 different sort of chain maps. Each of those chain maps is going to encode the different ways to impose point constraints. So given gamma embedded, pick a generic base point, P gamma, and we'll write it as overline to indicate if gamma is not embedded, then we look at its underlying embedded iterate, and this is going to live in the image of gamma, which is and then the way that I'll set up my differential is overall it will go from NCC star to NCC star minus 1. It's a little bit confusing how to think exactly of the grading because of this formal symbol business, but it works out if you interpret gradings correctly. And then you have a matrix. This is D plus D. Check. Minus. Okay. So what you want to do is kind of think you have some differential. The hat and the check, depending on where they sort of appear, if they're the input or their output, that will correspond to if you have point constraints or not. And so D check is going to eat a checked Rabe orbit and spit out a checked Rabe orbit. D hat will eat a hatted Rabe orbit, spit out a hatted Rabe orbit. And then these guys are the other two. This D plus will kind of look like the map in symplectic homology, which sends a Rabe orbit to twice itself if it's a bad Rabe orbit and 0 if it's a good Rabe orbit, and will correspond to having 0 point constraints, and then D minus will correspond to having 2 point constraints. Okay. So here, a hat is typically going to correspond to a constraint at the bottom if on the minus infinity end of a cylinder, and a check will have a constraint at the top if on the plus infinity end. Okay, so D check, alpha check, beta check. This is going to count cylinders, and because we have a check at the top, we're going to have a point constraint at the top. So we have ev plus is equal to p alpha. And then we also have to have Morse-bot buildings where you can have more than one level and you just need sort of a cyclic ordering. So this kind of corresponds to the cascades that you would get, where the cascade is corresponding to a cyclic ordering condition, where you have ev minus, ev plus of the next cylinder, and then the point constraint, the generic base point. So you have ev minus, ev plus, and then the point constraint, base point. And it's ordered by the Rabe flow. And then here, the index difference between alpha and beta is going to be equal to 1. And because I have a point constraint at the top, I'm going to have the virtual dimension of my moduli space, which is 1, will be cut down by 1, so it'll be 0 dimensional. So this will give me a finite count of elements. And d hat will do something similar. But now I'll have a point constraint in the bottom. And I still have these more spot buildings. Okay. And what's kind of interesting is that if you have enough transversality to use a time-independent family of j's, then this coefficient is going to be the coefficient of the Eliashberg-Giventhal-Hofer differential, which encodes the multiplicity of the top orbit, which gets seen because of this evaluation map at the top is going to see the sort of multiplicity of the cylinder and the orbit, and you'll need to divide by the multiplicity of the cylinder to count correctly. And then this second differential, this d, or it's not a differential, the second chain map d hat is going to, the coefficient is going to correspond to the Eliashberg-Giventhal-Hofer one, where you've encoded the multiplicity of the bottom Rave orbit. Okay, so then, let's see. Okay, so I have two differentials left. So d plus alpha hat beta check. This counts cylinders which do not have any base point constraints, plus your more spot buildings. And here you have the index difference between alpha and beta is equal to 0. And so the point is that if, again, you could pick your family to be time independent, then the only sort of moduli space that you should be able to get where the Conley-Zander index of the top is the bottom, to get that it's zero-dimensional because you have no point constraints, that would have to consist of trivial cylinders. And so then that gives you the 2 if your Rave orbit is bad, and 0 if your Rave orbit is good when you count. And then the last guy is what's sort of similar to the U map, and it shows up in sort of the long exact sequence involving symplectic homology, and you can use it to prove a lot of interesting sort of dynamical things. So this counts index difference 2 stuff with 2 point constraints. So you have a point constraint at the top and the bottom. And the thing that's interesting is that you need to have an obstruction bundle gluing correction term in the presence of contractible Rave orbits. So sort of, even if you do have all the transversality in the world, you're still going to end up with an obstruction bundle gluing correction term, which is kind of like analogous to why the ECH differential is so interesting. So let me sort of quickly say what this obstruction bundle gluing correction term is, and then I'll explain kind of how we can relate this non-equivariant theory to the original theory of Eliashberg, Giventhal, and Hofer. Okay, so what's going to happen is that the obstruction bundle gluing term, so we'll have d minus of gamma is going to be elliptic, and then we're going to look at its d plus 1 cover, and then we're going to look at the formal object that's associated to H0, which is a checked guy. And then we'll look at the hatted guy that corresponds to the d-fold cover. And so the idea is that this is a particular elliptic orbit that gives rise to an index 0 branched cover, which is a pair of pants. And because it's a branched cover of a trivial cylinder, there's no way to perturb it to get rid of it. So even all these sort of abstract perturbation schemes, because they can't sort of account for these trivial cylinders from appearing because they've perturbed them away, that tells you that sort of the count that's naively expected is not actually going to be correct. And you have to really go back and look at what obstruction bundle gluing tells you to glue this branched cover together to get that d squared to 0. Anyways, okay, so this is going to be gamma d plus 1. This will be gamma d plus 1. We're going to have a point constraint at the top, So it's a check. And then this is an index 0 pair of pants. This is a gamma, where this is a holomorphic plane of index 2, meaning that the Conley-Tander index of gamma is equal to 3. And then you have an index 1 cylinder. So this configuration is counted by, when you look at d squared, you'll have a term in the lower left-hand quadrant. So you have plus d minus d hat. So you multiply this out. And then in this lower quadrant, you'll get d minus d check, and then plus d hat d minus. And because of this living in this lower quadrant of d squared, that's going to have to count index difference 3 cylinders with a point constraint at the top and bottom. Because then you're going to get an index difference 2 cylinder. You divide out by r, and now you've got sort of the right dimension, and you've got the right point constraints. So that's going to be, of course, you have to consider this moduli space of index difference 3 curves with 2 point constraints. That gives you a space of index 1 curves. And if you look at the compactification of that space, you need to understand it. But unfortunately, it can break into this kind of a configuration. But fortunately, from Michael's work with Cliff, we know how to count it. And this is going to be given in terms of the degree of a winding number from the moduli space of index equal to 2 planes asymptotic to gamma. And we've modded out by r. And we look at this moduli space. We can look at it as a map to the complex numbers, take away the origin, modulo r greater than or equal to 0, and that's S1. And then you can look at the degree of this map, and that's going to give us the sort of correction term. And so in sort of the Bourgeois-Ashberg-Ekholm paper, they don't have a correction term here, which is needed in order to have those sort of algebraic formulas for surgery and stuff work out. And the sort of idea is that even though you're using time-dependent, almost complex structures, you can still have a time-independent building bubble off. And so that once you know that you can have a time-independent building bubble off, then you have to incorporate that into your compactification. And so you have to understand how to be able to count these configurations.
Uh-huh. Do you have the exact same thing when you do positive homology?
You should, but people haven't because positive symplectic cohomology, the way that you compute it is in terms of all these spectral sequences, you can't actually sort of see that term appear somehow. But it is it's kind of like how you don't see the obstruction bundle gluing terms appear in the Seiberg-Witten theory side, but you know that they appear somewhere. So when you're trying to sit down and prove an isomorphism between a contact homology and the positive symplectic homology, somehow you need to be able to understand where this obstruction bundle gluing term comes in. So that'll be future work. Okay. So then the theorem that's on the archive by Hutchings and I from June, we sort of didn't want to go through 90 pages and then explain what happens with the obstruction bundle gluing term in another 90 pages. So we first sort of restricted to the case where there were no contractible Rabe orbits. And then in a separate paper, we're going to treat what happens when you allow for contractible Rabe orbits, and then you need to understand how this obstruction bundle gluing contribution works. So we're going to assume that M2n minus 1, kernel of lambda is closed, oriented, non-degenerate contact manifold, and we're going to assume that it's hypertight, meaning that it admits no contractible Rabe orbits. then if J is a generic S1 family of lambda compatible almost complex structures, then this non-equivariant differential is well defined and it squares to 0. And moreover, the homology which depends on M, which in order to define depended on a choice of J and lambda, that actually this homology does not depend on the choice that you made of your lambda or J. Okay. And then the theorem that we're working on for 2020 is that if M3 kernel lambda is dynamically convex, then the above holds with the obstruction bundle gluing correction term. Okay, and then the idea is that it's expected that if your contact manifolds admit a symplectic filling, then this non-equivariant contact homology should be isomorphic to the positive part of symplectic homology. But this isn't proven. So that NCH of M lambda, well, I guess this is C, and then, I don't know, you want, yeah, okay. This should be SH plus of the filling, and then you have some symplectic information attached to the filling. Okay. So in the last 10 minutes, I'll quickly sort of connect back with the theory of Eliashberg, Giventhal, and Hofer. And so there, what we do is, okay. We mimic a family Fleur construction in order to construct an S1 equivariant version of contact homology. So we want to mimic the Borel construction, which is also called sort of family Fleur, which appeared sort of in quite a lot of detail in the work by Bourgeois and Wansha when they formally constructed S1 equivariant symplectic homology. And so you need to enlarge your family of J to be it's going to be an S1 cross ES1 dependent S1 equivariant family of J so that you can do this construction. And then your moduli space is going to sort of have these, it's going to consist of both sort of flow lines on CP infinity and sort of it's going to hybridize these flow lines with pseudo-holomorphic curves. But because you have this, because you're using a domain-dependent family of almost complex structures, you can still get the transversality to work out. Okay. So you're going to have flow lines eta and between x plus and x minus, which are corresponding to critical points on S infinity. So this is eta is going to map from R to ES1, a flow line on S infinity, and so you can think of x plus and x minus as coming from critical points on CP infinity, and then you lift them to S infinity under the sort of canonical projection. And then your J holomorphic curve equation depends on this eta. So you have J, T, eta of S, dt, U. Oh no, this is a Z. Yeah. And then you have the limit as S goes to plus or minus infinity of eta of T equal to pi inverse of x plus minus, which are the critical points on CP infinity, plus sort of the Rabe asymptotics. And then you need to mod out by the automorphism group of S1 cross R. Okay, so this is some kind of even more gross moduli space than before, but it's kind of like a standard trick, and once you get used to sort of Borel constructions and family Fleur constructions, you're okay with it, and it consists just of somewhere injective curves, and so you can use it to define an equivariant differential. Oh, this is in general. So this theorem doesn't. I mean, I guess probably most hypertight contact manifolds don't have symplectic fillings, but this doesn't have a restriction on the dimension. And then if you want M to have contractible Rabe orbits, then you need to be in dimension 3 and be dynamically convex. Okay, so then the theorem that Michael and I proved in this preprint from June is that under the same assumptions of hypertightness, then for a generic S1 equivariant S1 cross ES1 dependent family of almost complex structures J, you can get a chain complex by taking the non-equivariant chain complex and tensoring it with the cohomology ring of CP infinity, which is just generated by formal variables of degree 2. And then your differential splits into sort of a term that counts pseudo-holomorphic cylinders, which may or may not be parametrized by flow lines. They'll be parametrized by flow lines if the index sort of difference in your critical points is more than 0. And all right. What do I want to say? So here, this D0 is going to count exactly what NCH counts, and this D1 is going to be a BV operator. And then you have sort of higher order terms. So this forms a chain complex. And the homology is independent of the choice of lambda and J. So you get a legit contact invariant. So then what happens is that in dimension 3, you have sort of just enough regularity to use a time-independent almost complex structure. And when you do that, you can do a little spectral sequence trick to relate what the S1 equivariant contact homology is to the Alyashberg-Giventhal-Hofer theory. So theorem is that if dimension of M is equal to 3, then you can take this family J to be a single J. All the higher differentials are going to be 0. And this BV operator is the usual thing, where D1 of alpha check is going to be M of alpha hat if alpha is good, and 0 else. And D1 of alpha hat is going to just be 0. And then, so what's kind of nice is that so we can show that in dimension 3, there's enough transversality to define the moduli spaces for a generic S1 independent choice of lambda compatible almost complex structure. And then basically everything drops out. And we have a simplified expression for D0, which is the nonequivariant contact homology differential. And then using a little spectral sequence argument, you get that CH S1 of M lambda J tensored with Q actually gives you the original sort of contact homology theory proposed by Eliashberg, Giventhal, and Hofer. And the other thing that you need is that the CH star S1 with this M lambda J, it actually agrees with CH star S1 of M kernel of lambda coming from this theorem. And the reason for that is because you can take a small time-dependent S1 equivariant, S1 cross ES1 dependent family of almost complex structures, which is nearby your time-independent J. And you know that because you've now introduced time dependence, you get a contact invariant, but sort of the implicit function theorem tells you that the counts in the independent case have to be the same as the counts in the S1 dependent case. And so you can get invariance of the Eliashberg-Giventhal-Hofer theory in this roundabout way because you've been able to relate it back to Borel construction, which is a contact invariant. And then we get more information because our chain complex is defined over Z. You include the Batoréo orbits. It's a bit more clear how to relate contact homology to sort of the symplectic homology realm. And I guess our work for 2020 is to basically allow to relax this hypertight condition and see what happens with the obstruction bundle gluing terms. So I'll end there.